An inelastic collision is one in which the work done by non-conservative forces is negative, indicating that some of the mechanical energy of the system is converted to non-mechanical forms. So some mechanical energy is lost, E decreases. This category would include almost all collisions between real objects. Anytime two things hit and they make a sound, or they generate some heat, or they deform in a permanent way, you're converting mechanical energy into non-mechanical energy. Another possibility is that the work done by non-conservative forces is actually positive, indicating that some non-mechanical energy is converted into mechanical energy. So the system gains mechanical energy. This would include a reverse collision, or in other words, an explosion, or any kind of engine-driven system. So we'll discuss this as well. For comparison to our discussion with elastic collisions, let's look at a two-body inelastic collision in 1D. So B and C come at each other and collide, but not in a springy or elastic way. So we can write our equation for conservation of momentum. No impulse exerted by net external forces. So the change in momentum of the system is zero. Momentum will be conserved in this collision. So we can express momentum conservation as the sum of B's momentum before the collision plus C's momentum before the collision equals B's momentum after plus C's momentum after. Now let's imagine that we know the masses beforehand and we know their initial velocities, and we would like to be able to predict the outcome. We want to predict the two final velocities that I've highlighted here. Can we do it? Clearly this is just one equation, so it's not enough information to solve for two unknowns here. So let's express what we can about energy conservation. Our premise this time is that the change in mechanical energy is non-zero because there is non-zero work being done by non-conservative forces. So we could write that the change in B's kinetic energy plus the change in C's kinetic energy equals the work that's done by non-conservative forces during the collision. And now we've got two equations, but we have three unknowns: the final velocity of B, the final velocity of C, but also, in general, the work that is done by the non-conservative forces during the collision is not known to us beforehand. This is not easy to predict. And so if we don't know how much work is going to be done, if we don't know how much energy is going to be lost in the collision, then we can't predict the final velocities. So this is in contrast to our elastic collision, where we would be able to predict these with certainty, knowing only the initial velocities. Here, we can't do that. So these two equations are true, and they may be useful to us, but there are too many unknowns to predict the outcome in an inelastic collision in general. Having said that, let me introduce an exception, a special case. The special case that we call the completely inelastic collision. This is when two objects collide and then stick together and afterward move as one. So we have B and C coming at each other with some unknown initial velocities. They hit and they stick, and then they move off together as one combined object afterwards. We can express momentum conservation like this. Here's the initial momentum of B plus the initial momentum of C. And then afterwards, if they've stuck together, they make effectively one single object with combined mass, mb plus mc, moving off with some final new velocity I'll call v2. But inspecting this equation a bit, if we divide both sides by mb plus mc to solve for v2 to try and predict the final velocity here, we get this expression, and we notice that the numerator is, of course, the momentum of the system. Momentum of the system before equals the momentum of the system afterwards. And the denominator, that's just the total mass of the system. So V2 is the total momentum, the momentum of the system over the mass of the system, which we identify as the velocity of the center of mass. We're proving here that in a collision in which the objects stick together, their final velocity will be equal to the unchanged VCM of the system, the VCM that was the same before and afterwards. So they stick together and move off at a final velocity that is the VCM. That's an interesting result, and we can predict this final velocity if we know the objects will stick together. So this is the one kind of inelastic collision where we can predict the outcome beforehand, if we know they'll stick together. But why do we call it completely inelastic? Let's look at the post-collision kinetic energy of the system. So the final kinetic energy is 1/2. Here's the total mass of that combined object moving off as one, and its final velocity is going to be the VCM. We can notice that this expression, 1/2 times the mass of the system times the VCM squared, that could be written as the total momentum of the system squared divided by 2 times the mass of the system. The mass of the system doesn't change, and the momentum of the system doesn't change, and we see that this quantity is exactly what we have called in the past the kinetic energy associated with the center of mass, the KCM. That's the portion of the kinetic energy of the system that only external forces can change. So all that's left after this stick-together collision is this part of the kinetic energy. So in this stick-together collision, the system has lost the maximum possible amount of kinetic energy. It's lost some kinetic energy. How much? It's lost all of it except for this. This is the kinetic energy it still has. The kinetic energy associated with the momentum, which is exactly the kinetic energy that it couldn't have possibly lost in the collision, because only an external force can change the momentum of the system. So our system has lost all the kinetic energy that it can, leaving it with only the KCM that it cannot lose on its own. So this collision is as inelastic as possible while still conserving the momentum of the system. So in this collision, the work done by non-conservative forces was as negative as it could possibly be. We lost the most mechanical energy that we could while still conserving momentum. That's why we call it a completely inelastic collision.